Okay, thanks a lot, Stefan, and thanks for showing up. That's great. Okay, I'll talk about capacity expansion models today with a grand title. Let's see if it can if I can match the title here. But before we get started, let's start with a riddle. So here you see a container filled up with small lithium-ion batteries, and up there it's an illustration of two lakes in the nature connected by a subsurface waterway with a reversible turbine generator set. So the riddle is, what's the difference between those two? You don't see any difference? Well, I don't either, not if I look in my capacity expansion model. Okay, so for those of you who know capacity expansion models, you know what I talk about. The others you'll see. So I will base my presentation on a recent publication in Nature Energy, which was a result of a digital workshop held by Argonne National Labs in the US, where they invited several researchers around the world that works with both capacity expansion models, energy economics, and also energy storage analysis, and we had many presentations and workshop discussions on how to model energy storage devices in energy system analysis tools, and it resulted in a quite nice kind of review paper or overview paper of the challenges and possible solutions to get a better how to improve energy system analysis models, and why it is important to add storage devices in a proper way to inform decision makers on possible energy transition pathways. And I am just in the middle of the authors here. The lead authors were Todd Levin and Audun Botterud from Argonne National Labs. Audun is also at MIT, but this work was part of his Argonne job. So what's important is that the tools that we make, they are suited for the challenges ahead, and all the planning tools that we work with, they presently we work with them in a way that they should help to find strategies or difficulties in reaching decarbonization goals for the power system. That's most of our work is now targeted towards, and the ambitions of zero carbon power systems means that all the different parts of the power system needs to change. The supply will go from fossil-based thermal generation towards being dominated by variable renewable sources, not the sole ingredient, but the major part, and most of it will be connected with inverters, making system stability a different challenge and more challenging that we've seen before. The demand will both change and increase due to electrification. We need to take into account the new supply and demand patterns in our planning and operation of the power system. And finally, it's not enough to just kind of work with system optimal models and plan like governmental plans for build out of renewables. We have to have market designs that makes it attractive to invest in the right technologies, and also that gives the right price signals during operation. And what kind of role can capacity expansion models play in this? Well, according to us who work with capacity expansion models, they are super important for this. And they actually are. They typically try to come up. We try to come up with scenarios on how the power plant fleet can look like in different zero emission or low zero emission scenarios. But in order to get such results, you need to not only build a detailed model, or at least a quite detailed model of the power system. You need to have input data that you trust, and some of the input data you in scenario studies you cannot trust because they are scenarios themselves. So for instance, here it's quite many of these technologies have known costs and technology performance, except for energy storage on top here, because we typically assume energy storage characteristics and costs that is not what we have present today, but we assume some kind of technology development. Same also goes with wind and solar, although the basis, the cost basis, is much clearer for these technologies. So we need input data, but not only on the technologies, but also on all the surrounding system. The demand that needs to be supplied is the driving factor of the analysis. For the model itself, I will come back very soon with the details on how to build up the model and what kind of difficulties that we face. And then it's the analysis of the results and the decisions that ultimately can be made as a result of the analysis. And of course, then we have to also be sure that we can not only trust the input, but we have to trust the output before we come with some advices. So I say, yeah, my model shows that this will be a good mix of power technologies to go forward with. Then, okay, I should really trust that model before I give this advice. What if I have made an error somewhere here or somewhere here that totally changes the results that come out? So we need to have a good feeling also about the technologies and the system that we work with in order to be confident in our results. So here we also see that this is like a stage-wise development, and I think one of the more sophisticated capacity expansion models that we already have, like Empire and Times and so forth. Many of you in the audience know Empire either by presentations or you work with it. Here is an example on how a large capacity expansion model can be used to come up with transition pathways from existing power plant fleet to a net zero power plant fleet at minimum cost, given the input data and model assumptions that we have. Because the power system is going to be, according to the ambitions, going to be net zero here. And this is one result of this, but of a large capacity expansion exercise. But you don't see any energy storage here. This is just the energy or the power generation technologies. It doesn't say anything about how this is balanced. The difference between demand and generation is balanced every hour. So I will therefore go with the basic formulation. So I said something about how to do it in the title. So okay, so let's look at what exactly is a capacity expansion model with energy storage. Those who have had the power market theory, you might already have seen the formulation, but I start with a drawing from one person in the audience here. It is 23 years old drawing of a renewable hydrogen energy system, and starting up as a pure electric energy storage, but adding the nice car here also from Christian here to make it an integrated energy system. So, but my example is just without the car to make it simple. We have a demand that is going to be supplied by one wind turbine and supplemented by an energy storage, in this case hydrogen storage, and the capacity expansion model that we now will look at is just going to find the system components that minimizes the total cost. So we have a problem formulation, the typical capacity expansion model, find component sizings, which gives the lowest total cost. The only operational cost that I set here to make it super simple is just a penalty cost for not served energy. I don't have any other thermal generation with any marginal cost. It's just to minimize the cost of unserved energy plus all the investment costs for the different equipment that I have. So I have a set of decision variables, the capacities, and input parameters, specific cost, in addition to cost of non-served energy, and the time series for the wind power, scalable time series for wind power generation, and a time series for the demand. And the capacity expansion model then looks like this. This is the mathematical equations that solves this problem, finds all the components that minimize the cost, assuming that we can use linear parameters for all efficiencies, and that the power output is of the wind farm is scalable, and that the demand is known and inflexible. And now I come back to why the lithium-ion battery container and the pumped storage system is the same as the hydrogen storage. They all have the same three equations here that defines its operation. And then, of course, my next question then is, okay, is that a sufficient technology level to build advice on? Yeah, we should be a bit, we should bear that in mind when we use the models. Are they too simple or are they okay? Let's see if we can find some evidence on that. But before going into the details, I would now say a little bit more about why capacity expansion models can matter, why it's important, how we can use, or I hope not abuse the results, because I'll now show some examples on what kind of insights we have got from working with capacity expansion models, using the simplified basic model that we have here. I think most capacity expansion models that are used in practice have this type of equation for the storage device. The only difference between different storages is just the parameters used. So an efficiency of the different energy storages and the specific cost of the components is what that makes them differ. So I start with let's say a bit of a blown up variant of the simple model that I just showed. It's from actually from a master thesis of Magnus Askeland, now at SINTEF. He made an equilibrium variant actually of the model, but it's basically a capacity expansion model, a linear capacity expansion model, just as I showed. The aim here is to minimize the annual operation and fixed cost of a North European aggregated power system, given a scenario for wind and solar. So wind and solar capacity expansion is not part of this study. So the variables are just the component sizing of the three variables, the flexible units here. And flexible units, we have gas power, coal power, nuclear power, and batteries, and Norwegian pumped hydro expansion. So we then, for the pumped hydro, we have identified pairs of lakes that we can build new pump stations between. Some in the audience here are working on more detailed models than this as we speak. And the amount of wind and solar is given in this scenario. So the question is how to build flexible resources around the North Sea that minimize the cost of delivering the net demand. So I first run the expansion model without any energy storage, and we see here a nice combination of different thermal generation. Nuclear serves as the base load, and then we have coal and combined cycle gas turbines as mid-merit plants, and then open cycle gas turbines at the top. They are cheap to install but expensive to operate because of low efficiency, completely opposite of nuclear with low operating costs and high investment costs. Then we add the possibility to invest in pumped hydro with assumed costs for cables and installation of reversible turbines and building tunnels between existing lakes. We see that Norwegian pumped hydro replaces some of the coal and boosts a little bit of the nuclear. And this is not a big surprise. This is how the French system is built. They also do have some flexibility in the nuclear, but typically they try to run the nuclear at as base load, while pumped storage takes the balancing. So it's an attractive combination. We also have, I could say that to give a perspective, the amount of wind and solar here is enough to cover 40% of the energy demand. So it's like a rather well-developed renewable supply system, but it's not like 100%. It's more than we have today, but not like fundamentally different. And then we remove the possibility to install pumped hydro, and we install batteries instead. And we see that the batteries, they take the capacity, some of the capacity of the gas, the open cycle gas turbines. So they are used for fast response. So they take the short-term flexibility, while the pumped hydro with much longer energy storage capability, but with a bit lower efficiency. They take the longer term balancing needs. And when we add both investment opportunities together, we see that they are not competing. They take each of their slice of the fossils, making a more efficient integration of the wind and solar here. And we actually also see that nuclear CO2 emission-free fossil thermal is keeping up. So it kind of eats from the fossil from each side. And we can explore the reason why when we look at the details of the capacity expansion model, because it's optimizing the operation every hour of the system deterministically, but still we can explore why this happens. So the battery is charged and discharged many times during a week, once a day, while the pumped storage has a typical seasonal pattern. So it's a nice complement. So it's a finding that these two technologies are not like competing storage technologies. And looking at batteries, I would show another example of technology complementarity is how we have used capacity expansion models to investigate the how and why PV and batteries fits together. So this is a study from MIT, but I was part of it as a part of my sabbatical. So we used the same type of model, but it's a GenX model that many of you, but not all, have heard of. It's another capacity expansion model, just like the one that we just saw an example of. But here, the wind and solar investments are part of the variables and non-variables. So we use then scenarios for costs of all available or relevant technologies for a study of Italy, because this was a study for I think for Terna in Italy, and looked at how to achieve a zero emission power system to cover the Italian demand, given then the Italian wind and solar resources and some hydro and some thermal available, some thermal alternatives. And here we have then used a CO2 constraint, so we can use a capacity expansion model and set a constraint on how much CO2 that we allow. So no limit, that means that there are no CO2 tax, and still we see that the I think we used cost scenarios for 2040, we still see that wind and solar takes much of the power generation just because it's cheaper than fossil, given those scenarios, even without CO2 emissions. So adding battery as an investment alternative in this system, then we have to assume cost for the battery. So if we just used 2020 cost, it would not change because it wouldn't install anything. So we assumed NREL projections for battery cost reductions for the, I think, next 10 years or so, and then run the model again with battery as part of the investment alternatives. And we see here that the thermal generation, fossil generation, is now cut in half. It wasn't much before, and it's even less now. And we see that we change from the wind dominated energy supply. This is capacity, and the capacity factor of wind is higher. So here, without batteries, wind is dominating the generation. But with battery, we see that it complements PV, because of its cost characteristics, it's beneficial to have like 3 to 8 hours, maybe 3 to 4 hours of storage, which combines very well with the daily cycle of PV. So we see that we also get a shift from wind to PV when we add batteries. There are other interesting details to be found that kind of might be contradictory to what we think of why we have what batteries can be used for, because what actually happens when we add batteries, then we get so much more solar. It's attractive to build so much more solar that the curtailment of solar power actually increase, because it boosts the amount of solar power that makes curtailment. That means as a percentage of the available generation, the renewable or the PV curtailment actually increase as a result of the combined benefits. It's not a bad result, but it's opposite of what we think, because there's a lot of PV curtailment, then we can install batteries to utilize the curtailed energy. Yes, isolated, it works like that, but if you look at the long-term cost minimized system, it's better to build so much PV that more of it is actually curtailed when you don't need it, because during the rest of the year it's beneficial to have this amount of solar power installed. So more batteries, more curtailed renewables. That's a finding. I hope it's correct. Yeah, I will not go into details of this rest of the study. I don't have time, but it's an interesting study. I recommend it if you're interested in energy storage economics, because we do some sensitivity analysis on the economics of long-term storage. This is a topic of very high interest in the US, especially both the analysis of long duration storage and actually defining what it is, and trying to develop technologies that can store electric energy for a long time. But we find out that the value of storage duration is kind of diminishing in the way that it is much more crucial for the system to have enough short-term flexibility and short-term storage. The longer the duration of the energy storage is, the lower the cost must be in order to be beneficial for the system. If you have the short-term storages, makes value to the system almost immediately, but the longer duration is much harder to get a good economic result for. I'm not surprised about these results, but considering the discussion and priorities of in energy research, now it's a hot topic to talk about. Okay, what to do, how to create long-term storages to deal with these Dunkelflaute events and so forth. And my immediate answer to that is to, yes, okay, build some reserve capacity to take care of those hours and months, thermal capacity that can do it. This is kind of what I read out of the results, but others come to other conclusions. Okay, so next and the final part, I will. Yeah. Yeah. Okay. Yeah, because you want some discussion. Okay. So how to make these models more realistic? Okay, I'll just give like rules of thumb. First, you need to have as a basis as many weather years you can. Don't make an assumption of one single weather year for wind and solar. Yeah, so if you use the wrong weather year, you end up with a lot of building a system that have a lot of load curtailment because it exactly covers the load, but you don't know. So you have to have a strong weather base. Next thing is do an evaluation of how important the energy storage is for tackling short-term balancing needs and uncertainties, because energy storage can be designed or can be operated also for balancing markets, reserves of multiple markets that will impact its optimal capacity. Typical capacity expansion models only deals with the hourly energy demand, and you get a system that is kind of optimized for that. But you need to also take into account that the batteries or energy storages can be used for balancing and reserves. Yeah, one of our previous PhD students, Espen Bødal, he made a model taking then formally into account stochasticity in the capacity expansion models. This is something, if you like difficult mathematics, this is something to continue working with. But it was a great work, but it's too complicated for me. Another thing to be aware of is that I think that battery degradation should be default in capacity expansion models. You have to take into account that. So that's the short story of the slides. I don't need to show. Just make, even though it's a simple linear model, battery degradation is important. Yeah. So the evidence is clear, but you have to trust me. So regarding the short-term, so storage opportunities, the balancing, how to do this in a simple way, that is the problem. Here is an example from our article where we have made capacity limitations of the state of charge to give headroom for reserves. So this is a way to add restrictions that take into account that the battery can be used in other markets, that you leave some capacity and put a value on that and you calculate the value of that, instead of including all the market opportunities in one model, which then makes it unsolvable. Final, I jumped the energy system integration, that is not so important. Yeah. My final slide before the wrap-up is, are we making the right assumptions when we create the energy system models? So this alkaline electrolysis plant is easily converted into one efficiency factor and one cost of capacity. And it's a question whether this is good enough. It can be good enough, but you should know what assumptions that you make. So to wrap up, the last part is that I would emphasize the physical representation and go back and check, okay, are we okay with the linear representation? And you should be able to explain why, and then try also to validate the model or read about model validation experiments of similar models that you have made. Every model doesn't need to be validated if you use the same principles as others, but be aware of the errors that are inherited by the say by the way we usually formulate the physical representation. And here is then also then a set of challenges for energy storage representation and capacity models that will not make this topic disappear in research and academia for a quite long time. So I'll stop with that.